and last talk in the series on local and topical.
Great, thank you, Jonathan. Thanks for coming. I've been enjoying Warsaw. So I'll try to make this talk as self-contained from the other, not depend so much on the other talks, but some properties will appear, and maybe you can make connections. So mostly, so we are talking about topological entropy. So topological entropy is a notion of chaos or disorder, but it doesn't. It's not what some people call global chaos. It's because imagine you have here some system, and here you have some a horseshoe or some full shift or something. Here you have something with some entropy, and then outside this region, the system can be very simple, and still the complete system will still have a positive entropy. So the positive entropy, you only need to have like a small portion of the system to be to have this kind of diversity in order to have positive entropy. But nonetheless, you can play. If we want to make some global notion, so we can do the trick a similar trick, such as K-system. So topological K-system. So this we call a topological dynamical system has completely positive entropy if every non-trivial factor has positive topological entropy. Okay, so in the measure category, this is so if you want every measurable factor to have positive entropy, these are called K-systems or Kolmogorov mixing, and there's a lot of characterizations about there's some probability versions using 0-1 law, or or you can see it as kind of some uniform way of mixing. So the particular question I want to...
I think I imagine you introduced notion of Pinsker partition.
Yes.
So 0 and checks that
Yes.
Pinsker partition is trivial, and the proof is like hop.
Yes. And actually we will talk about some sort of topological Pinsker. So the question I want to the question I want to attack today is this kind of, I think this was maybe asked by Pavlov in some sense. Is there a countable family of factors where, so I'll call this property CP, where CPE can be Okay, so because this is kind of like, okay, I have a system, I want to check if the system has completely positive entropy, but then there's many factors. And then to simplify the problem, I would like to know if there's a countable family where if I check within this family that every factor has positive entropy, then I'm done. So this is the main question that I want to talk about today.
You mean from which CPU? Because the way you wrote it, it's like you want to check if the factor has CPU.
Yeah.
But you want to...
From which, yes. And for measure category, the answer is yes. Because it's enough to check some. You can take partitions, and then you can take some codings, and then you can take some symbolics. You can check this on symbolic systems. So here the answer is yes. So I'll already give you an answer. For topological in general, the answer is no. So I want to tell you how to approach this question. So this is one way to study when you want to characterize something with where the quantifiers lie on countable sets. This is something that descriptive set theory is. So we will answer this using descriptive set theory. In particular, not what some people call descriptive complexity, which is some like subsection of. So what? Let me give you a brief introduction to. So descriptive complexity is about this is kind of like algorithmic. So this part of the descriptive set theory, what it does is it takes a Polish space, and then it wants to classify the subset of the Polish spaces. And the way they want to classify is, okay, how difficult is it to check that a point is a member of this subset or no? So let's see some example. Take an interval of the real line. And now we want an algorithm that tells you if a point is on that interval or not. and the algorithm is x smaller than b, is x bigger or equal than a. Let's do open. It's the same. And then you check this property, then you check this property, and then you're done. So this is very easy. So then, what about open sets? So open sets, you can see it as a countable union of intervals, and then you can do the algorithm on each interval. So this will be we have countable algorithm. So when I use the word algorithm, I'm not being too precise. It's just some intuition. There's a part of this theory that can use Turing machines and things like this, but I'm not going to. This is kind of different. This is more like a countable. It's more about countable algorithms than Turing machines. And actually, in general.
So what is the question about open sets of R? What is this question? I didn't understand.
You fix an open set,
yeah.
And you ask, is X in this set?
I see.
And then we get what we get is a countable algorithm where we can check membership.
Yeah.
Mm-hmm. And actually, if okay, you have open sets and then closed sets. The algorithm is you can check if a point is not in the closed set, and then you can take countable unions of closed sets, and then you can take complements of the countable unions, and then what I'm doing here is I'm constructing a sigma algebra. So actually, in general, for a subset, there is a countable algorithm that tells you the current point is in. So, and this countable algorithm, another way to see the algorithm.
When you say
Yes.
When you say borrowed subset, how is it presented to your algorithm? So what kind of questions your algorithm can?
So I'm being vague. That's why I say, when I say algorithm, I don't refer to. This introduction I'm being vague because actually I'm not talking about a precise theorem. It's just an interpretation of the theory, but it's kind of useful and in general it applies. But maybe what I'll write here maybe answers your question. Can be interpreted as quantifiers on countable sets. So if you have some condition, your definition, you define something, and the quantifiers lie on countable sets, then this is kind of like what I mean by countable algorithm. So this is. So when we are working with descriptive set theories, this is something they always have in mind, but many times I ask for like a precise theorem and they never gave me one. Yeah. Okay, so then it seems that that this theory maybe it's good to ask this question, because in some sense, I mean, we have to pose the question formally, but somehow we are asking if the CPE property is Borel or not. I mean, we have to build the Polish space, we have to build the right, but just by looking at this, it feels like, okay, this is, I want to check if something is countable, this is kind of related to being Borel, and then this question is also about some countable, so maybe there's some way to state this. Okay, so what we'll do is the following. Okay, so to build Polish spaces of topological dynamics, we need to fix a topological space. So let X be a compact metrizable space. And the Polish space will simply be so I'll call it like this: TBS X is the set of functions that continues. Equipped with sup metric. So we fix a space, and then we take all the functions that go from the space to the space. So in a way, this is a Polish space. I mean, actually, it's more than Polish, but so we are comparing functions by taking the supremum over.
What do you mean by it's more than Polish?
I mean, the X is compact. I think this is also compact, right?
Yeah,
Yes.
this is even better.
So it's compact metrizable also, which is more than Polish.
Maybe balance space.
All maps from X to X?
Ah, from X to X, I see. Okay.
Is it compact?
Continuous, right? These are continuous maps.
Yes.
Okay, and now when say CPE X is going to be F DDS X such that XT has completely positive entropy. So this is so now the question is.
What is the relation between F and XT?
Sorry. Let's look at.
Yeah.
Okay, now the question is Borel subspace. Oh, yes. So this question depends on X, which X we pick.
This is not compact.
It is not compact.
It's not locally compact, it's not compact, it's very easy to see it. So for example, we always work with CX01.
I mean, you will have the single, you will have constant mappings also, so this will not be common.
But the constant maps, of course, it's a copy of it, but it's very easy to construct a family that doesn't have a.
Equal continuity will be listed.
Yeah, it's not compact.
It's not compact.
Yeah.
It's Polish.
It's Polish.
Yeah, it's Polish,
It's
but
also
it's.
not locally compact.
Yeah, you're right. Yeah. Okay, sorry, but what I wrote is correct. It's Polish. Okay, and now this is the question, and this will depend on the x. For example, there are some spaces that where CPX is empty. So, well, for example, if x is finite, if x is finite, CPX is empty. But there's also uncountable spaces where. So sometimes CPEX is real or even empty.
But I don't think I don't see how this is related to Pavlov's question, because it's possible that there is an algorithm which checks CPE on factors, and checking the CPE on the factor is not Borel. However, you can get away with checking on a countable number of factors.
Mm-hmm.
So in such a case, it's possible that CPE is not the Borel set, but still there is a countable algorithm using factors.
No, I mean this. If it's not Borel, it's going to be strong. It's going to any possible way that you with countable arguments will be discarded.
Yes.
Uh-huh.
I agree.
And the thing you have to check is that actually checking just positive entropy, this is Borel. So this is Borel property. So now if you want to check positive entropy, which is Borel, and you only need to check it on a countable set.
But the question is a little bit different, because it's asking, is there a countable family of factors from which CP can be varied?
Yeah, okay.
And you didn't specify what operations are you allowed to do on these factors. I just claimed that maybe you are allowed to do non-Borel.
Yes, okay. Okay, yes.
And then the question, of course, you could take the original system.
Yes.
Say, the point is, I think, is there a canonical way of defining
Yes.
these factors?
And actually, this is the way. This is more the way the question was stated. I mean, actually, the question was a very precise family.
And on which you are allowed to check what? CPE?
That he was.
So this does not answer the question, right?
No, yes.
Checking CPE might be non-Borel.
No, yes, it does answer the question. And actually, it even, for his particular question, even, even we needed less than proving not Borel. But, so because I'm not understanding your comment.
So I don't know what this canonical family is, but I imagine that maybe checking something on one of the members of these factors by itself is not a Borel operation.
Yes. I mean, you need.
And then I wouldn't expect, this would not contradict the fact that the family of CPs are not Borel. But still, the answer to the question will be positive.
So are you saying what happens if the family is not a Borel subset?
No, I'm saying I have some kind of algorithm, like some kind of oracle. So I have a countable family, and for each member of this canonical family, I'm allowed to ask the oracle a non-Borel question.
But the question that you're asking of the family is positive entropy. not.
Only if it. Okay. So this was not clear to me.
Yes. Okay.
Only
Sorry.
if it has positive entropy.
Yeah. So.
Okay.
So you check. You're checking.
Yeah. In such a case, I understood. Okay.
Yeah. So you have some, and that you're only asking positive entropy.
This is positive entropy. Okay.
Okay, so now this is the question: is CP a Borel subset? Okay, so and then so what we will prove is that we will show that well, not show, but because I'm not going to, if even in very simple spaces like the interval, where the interval is not known to be like a very rich dynamical space for continuous functions. It has a lot of restrictions, but even for interval, we will see that CPI is not Borel.
It's not what?
It's not a Borel subset of this one. Okay, so the first thing is there's a notion of every system has maximal zero entropy. And this is known as Pinsker factor. So a system has CPE if and only if Pinsker factor is trivial. So it's just 1 point. Because 1 point is always a factor. So now the first thing to start attacking this question is Pinsker, which is a way to understand the Pinsker factor. So which points have to be identified to obtain the Pinsker factor? And for this, we will use we can use the independence theory, and we say xy is these are called IE pairs if for every neighborhood ux uy ux y has independence with positive density. So this means there exists with positive density such that for every function so this is what we saw in the other lectures. And okay, now the difference here is, well, we saw independence of sets. Now here we're asking that, so you have 2 points, and it doesn't matter how small I take the subsets, I will find some independence in this. I will find a way, I mean, I can travel with independence between X, this neighborhood, and this other neighborhood. And the nice thing about this is now this will help us. This kind of pairs will help us build the constructed topological Pinsker factor.
Excuse me. Yes. So then E is some infinite set, right? So for any f from I or from finite subsets of I?
Okay, I wrote it from I just to be because if you just want upper density, that definition is okay. Mm-hmm. If you want the stronger version I gave you on the first lecture, then you define it with then you change the definition of density, but then you check on. Yes, it can be like this is okay. So like this is okay, but only with the weak upper density result. And the result I gave you last week, I think you were not here. So last week I gave a stronger result that uses finite sets, but for this is okay. It's equivalent to what I said.
I see.
Okay. So this there exists. So first we have this result that maybe is not that surprising based on what we proved last. And just the trick to prove this result is that it's kind of this lemma: if U B have dependence with positive density and then there exists So, no, we did this last week. We proved that positive entropy implies the existence of sets with independence. But this is a bit stronger because here we're asking the sets are very small. And so the main trick to go from big sets to very small sets, it's kind of this is the main lemma that is used. You can start going smaller, and you can still find independence. So this is more like connection with.
But then your U1 and U2, is there any restriction on like U1 and U2 when you're partitioning U into U1 and U2, or you're just taking arbitrary subsets?
Yeah, it can be any subset. I mean, if one of them is very small, then the other one will probably be the one that. Then here's another theorem of only if the smallest closed equivalence relation on x times x. Okay, so let's take a look at this result. So, why am I using a T invariant? So why am I using, the thing is that there's a relationship between functions and equivalence relations. Simply by saying, okay, 2 points are related if the function maps them to the same point. Now, there's a relationship between continuous functions and closed equivalence relations. And finally, if you want the function to be a factor map, so to commute with the dynamics, you need to be T invariant. So, I mean, really what is happening here is that if you take the smallest closed T invariant equivalence relation that contains the I pairs, you will get the Pinsker factor.
Contains E pairs means all of them, or at
Yes,
least
all.
Okay.
So if this equivalence relation is the whole product space, it means the induced factor is mapping, you're relating every point with every point, so the factor you get is just 1 point. So this is the, and this is like this is kind of the. So this we will use for the result. So when so first let me tell you something. Okay. Let's say I see the set of okay, so we start with the set of I pairs. IE xt is closed and T invariant. So we're good, except it may not be an equivalence relation. You may have 2 points that are entropy pairs, and later on I will show you examples. You may have 2 points that are entropy pairs, and these 2 points are entropy pairs, but these two are not entropy pairs. So then, I mean, the thing is we want to build the smallest closed equivalence relation that contains. So then we say, okay, let's make this. Then let's take this called I don't know what the name of when you take the smallest equivalence relation. Sometimes they call it plus. You say, okay, let's take equivalence relation, but then there's no reason why this is going to be, will still be T invariant, but now there's no reason why this will be closed. So you say, okay, this is not it. So then you take, okay, let's take topological closure. Now it's not going to be an equivalence relation, and then you can continue and. So let's so we say xt has CPE rank 1 if so imagine we are lucky and actually all the pairs are independence pairs, so we are done. Like this is closed equivalence relation, okay, this is it. So this will be the easiest case, so this is rank 1. And has rank 2 if we take this and this is equal to square. And then, well, you say we can continue similar. We'll define rank A if you need to take this operation n times, and then you get all the space. But actually, but then you can define a rank omega if the union of I'll just use this union But then we can define rank omega plus 1, because now we can take this union and we can take the closure, and I mean this may not be an equivalent, so this may not be closed, this union here, So then we want to close it, and then actually we can define CPE rank for any countable ordinal. And then this is kind of like now it's time to make the connection. So already, I mean, if you read like Hecker's book, I mean, once you start seeing ordinals, kind of descriptive set theory is kind of around the corner. And
The question, so any action will have some rank?
no, any action with a completely positive entropy will have some rank. Yes, yeah, maybe that was your question. Yeah, this can be proved with some. I don't remember. It's kind of like an old result. But yeah, good comment. As a rank. Yeah, this, I mean, you may not be done at finite stages, but there's a countable ordinal when you will be finished. And it's similar like with the Borel sets. Any Borel set in the Borel hierarchy, it's in some level of the Borel hierarchy.
I think it's maybe better to define for a general system the rank when it stabilizes, right?
Yes, actually in the paper that's the way it's defined.
And then what you get is actually the maximal, is the topological
Yes.
Pinsker factor.
Yes.
And that's why.
Yeah. Yeah. I mean, this condition is the one that is making it CPE. But if you just want when this stabilizes, then it can be done in general.
Do you have intersection between various ranks, different ranks?
Okay, so that's going to be the main point. That looks space. Then is not Borel if it's only if the for any countable ordinal gamma there exists in CP with rank bigger or equal than gamma. So now this is the connection. So now that we have this rank, and then this, I mean, there's different ways to prove actually that this space is not Borel. But what I like about this result is that you can forget about descriptive set theory, And all you say is, okay, I want examples. You say, okay, if you give me examples with a large rank, arbitrarily large rank, then you're done. So then this is and yeah. So I mean at least at least there was one paper that where they didn't care so much about the descriptive set theory, and they just built the examples, and then you get the result for free without doing any. I mean, so now you can get this result without reading Kekris. You just have to build examples. Okay, so let's. Examples. So first, if you have something kind of, for example, mixing SFT or a system with specification so if you have systems with very strong notions of mixing, then actually they have rank. They have rank 1. And the reason is there's the specification or mixing SFT is going to give you you can have jumps between the possible words with bounded and then you can switch like if you have open sets, then you can switch between them to find the independence. So then and this can be done for any open set. So then it's not too hard to show that they have rank 1. So in particular, this map.
Wait, but so you didn't add here the diagonal, so you're all the time
the diagonal. IE pairs have the diagonal. So there's a difference between entropy pairs and IE pairs, and it's the diagonal.
Ah, I see.
Yes, I didn't talk about entropy pairs, but entropy pairs don't have diagonal, and IE pairs do have the diagonal. So in some sense, it's sometimes easier to work with IE pairs. So this kind of modified tent map has rank 1. Now do this. I can do this. Okay, so now note 0.1/2 and 1/2, 1 are invariant subsets. And so this means that a point here x and a point here y cannot be an I pair. Because for I pair you need to, if you visited in some time in x, you should also visit this, you should also be able to switch. But here, how you're going to switch x for y? You cannot switch. So these are invariant subsets, and this implies that the if x is less or half and y is bigger than half, xy is not in I. Nonetheless, note that this invariant subset and this invariant subset basically behave like this one, which this one has specification. Hence, IEXT is equal to 0,1/2 squared union 1 squared. And now take the transitive not the transitive, take the smallest equivalence relation that contains this. Now it's going to be everything because they can always they share a point which is 1/2. So like for example, 0 is related to 1/2 and 1/2 is related to 1. So you can go from here to here. So now this is 0,1 squared. So this let's call this T2. So T2 has this. Now, if we do this trick finitely many times, it doesn't work anymore because the transitive, because once you take the smallest equivalence relation, it will be the whole. It will still be rank 2. So if you take this and this, it still has rank 2. So this is not good for rank 3. So then what you have to do is now take a converging sequence here and copy this sequence here, and now on each square in this now we copy this. And now the IE pairs are going to be same. They're going to be the products on each of these. Each of these each interval is invariant. And each ij squared is a subset of I interval T3. Now this is T3. But now, when I take, no wait, this is still going to have, yeah, because I defined the rank with, now, okay, so now the thing that will change here is that IE T3 closed is not going to contain anything with the you're not going to be able to get the one.
Because you are taking finite operations.
Yes.
That's the point, right?
Yes. So say 0, 1 is not contained here. So this now still has rank 2, but now it's a bit more interesting because here the equivalence relation was enough, and here now we really need the closure. Because now here we're only missing things related to 1. So when we take the closure, this is the whole interval S squared. And now, I mean, to not so the general proof, for the general proof, then what you do is you take a sequence that converges, but then you take another that converges, and you take another convergent, and in each of this one there's a convergent. So for the general proof, we build a connection between Cantor-Bendixson rank and CP. So we take subsets of the interval with arbitrarily large Cantor-Bendixson rank, and then we kind of do this trick here, but now this is going to look more weird, and this is how, and then with this, we conclude there are examples with large rank. Hence, CPEI is not whatever. Okay, so just I forgot a comment I wanted to say about this other proof. This proof here is so what we have to prove is that the CPE rank. So this is some remark that should be from before, that is something that if you look in Kekri's book is what is called pi11 rank. So this is okay. So
Is there like a natural topology on the ordinals? Well, I mean, you could take the discrete one, and then you would say, okay, we know that there is an uncountable number of countable ordinals. Maybe this is the reason. But maybe there is another. Because it would be like interesting to relate CPE I is not Borel with the fact that that you can get an arbitrary large rank, so in a sense the ranks that you get is not Borel, the set of ranks, something like that.
Yes, I don't know if this can be. Yeah, I'm not sure. So you want to put a topology on the ordinals,
Right.
to conclude the what?
No, like to make the, in a way I'm trying to understand the proof of the term that you didn't give the proof.
Okay. Yes, the result that I didn't give the proof, it's in a way we use some previous result that already does the, and this is what I wanted to say about the pi11 rank. So so for example, if you want to prove that Cantor-Bendixson, because this is kind of a similar proof to that on compact subsets of of interval, with the Hausdorff topology, the countable subsets are not Borel, and they use Cantor-Bendixson rank. And to get this proof, this is kind of like the abstract version of that proof. And they say, okay, we don't need really Cantor-Bendixson rank, all we need is some properties, and they call these properties pi11 rank. So then if you have a rank, and you prove that the rank is pi11, then you can get the result. But in a way, I think that the heart of the proof is very similar to this proof about countable compact subsets. Okay, so I don't want to say too much more. So some extra comments I want to say is, so there's something unsatisfying about this result, and that is that these examples are not transitive. So sometimes it's nice to have, because like transitive or mixing examples are kind of more, and actually there's something, if you have an example with, so this is the interval CP and mixing, then IT has rank 1. So the interval was good to get examples, but if you really want a mixing example, you cannot use interval because immediately you get rank 1, so you cannot increase the rank for but then what we did prove, and this was harder, that if X is a Cantor space, then mixing CP is not working. So if on the Cantor space we have more diversity, on Cantor space we can build examples with very high rank that are mixing. And so let me just give you the last example. So rank, for this case, rank 2 is easy. Well, not easy, but rank 2 was not difficult to build. Rank 3 was very hard. So once we got rank 3, we got all of them. But rank 2 is so first let me give you one that is transitive, not mixing, because it's simpler. So what I do is I take x1 is equal to so what I want is this periodic subshift. So we have 2 points, 2, 3, and the shift. And then x2, we take full shift.
What's the x1 is?
So it's just a very simple example. It's just, it has two periodic points. The periodic point that has 2, 3, 2, 3, 2, 3, and is the shift, and that's it. So, yeah, sorry, I couldn't think of a fast way to write this. And then, write y equals 1 in 0, 2, 3, such that each coordinate is equal to x1i, x2i with x1 in x1 and x2 in x2. And now what's going to happen here is that okay, so we have kind of 2, 3, 2, 3, 2, 3, and here we have 1, 0, 0, 1, 0, 1. So if you have a 1, you put the symbol. If not, you put 0. But then if you have a 2, like the 2 and 3 do not have independence. Because you cannot, if you see a 2 in some position, there's no way that, so say you see a 2 here and a 2 here. This means that the distance between 2 and 2 must be even. So then there's no way I can find a 2 Because this is independence, right? That you see a 2 and then I can find another with a 3. But this is impossible because the 2, 3 have a very rigid structure. So 2 and 3 cannot have independence because if I see a 2 and a 2, I cannot see a 2 and a 3. I'm not giving you the whole proof, but just the main idea. But 2 and 0 have independence with positive density. Because 0, see, in this, you have complete freedom because this is a full shift. So the 0 you can put wherever you want. And 0, 1.
So you just clarify, so this notation, number in brackets means
yeah, sorry.
cylinder with the...
Yes, the cylinder that in the center point has.
Okay.
So I'm not. This is not a complete proof, but more or less what this tells you is okay. There's points that are not going to be IE pairs, but there's one point that is 0 to infinity that you can switch with every point. So then it's like similar to the other example where they're kind of two separated. But now you can check that this example is, this one is transitive. This example is transitive. It's not mixing. With mixing we have to do some other trick, but this is kind of like for rank 2, this is, I think, kind of like the essence. Taking a product of two transitive systems, take a factor, and then on this factor you check the. So I think here I want to stop right here.
But wait, what about rank 3?
What about?
Rank 3.
No, rank 3 is no, rank 3 is very painful. Actually, once we had rank 3, we had the complete proof. But yeah, rank 3, we can actually rank 3 cannot be done in the finite alphabet. I mean, it's not that it cannot be done; it's that we didn't know how to do it. We had to extend, we had to grow the alphabet to infinity, and yeah, it's more, yeah, it's more annoying. You cannot do. It's not a cheap trick.
So this is done?
Yeah, I can.
So any question?
Yeah, my question was, if you have rank n, and n is greater than n, then you have an intersection or something?
What do you mean by intersection?
I mean, then there will be something which is rank this also and this also.
So it depends how you define rank.
Okay.
The way I defined it in the talk, yes, because everything with rank 3 has rank 2.
Yeah, that's what I
But in the paper we didn't define it like this. We defined rank 3, everything that has rank 3 but does not have a rank 2. So then there's no intersection.
Do you have some examples which has all the ranks?
No, I mean we have examples on every, yes, we have examples on every rank. But you cannot have an example that has all the ranks.
Yeah, that's
Right, but because they stabilize. There's a result. I don't remember which result. You have to use kind of like an old result, but they always stabilize. I mean, you cannot have. This kind of stuff at some countable ordinal.
Stabilization has to do with separability. You know, when you have a sequence of
Yes.
relations that are contained.
Yes. Yeah, I guess that's some result like this.
That's completely standard.
Yes.
How sensitive is your theory to the fact that you are working with Z?
No, I mean, my feeling is that when it comes to upper bounds, when it comes to lower bounds, the simpler the group, the better the result. So it will be, I think it will not be hard to put other groups there.
Also for mixing?
I think so, yes. Yeah, for mixing, maybe we have to think about mixing, yes. But in general, my feeling is that because for lower bounds, it's about building examples. So sometimes the bigger the group, the more examples you have available. But I don't know. I mean, maybe there's with the mixing. I don't know. I have to think about it. But my feeling is that it will not be a big problem. But I mean, these things have to be checked because sometimes you say, "Oh, it's easy," and then there's something very hard that. But in general, I mean, this is my feeling, my personal feeling that for upper bounds.
I guess my question is, if G is Sophie, and you use the CPE with the definition of topological entropy for Sophie code,
yes.
Is it true that CPE is not borrowed?
So here, I think it should be. I think I should be okay. I think the part that will be tricky will be the upper bound, because to prove that is because well this I didn't talk here, but actually these subsets are coanalytic. I think if we have Sophic, proving coanalytic, we'll have something like what happened that in what we're doing. That because now to prove upper bounds, the bigger the group, the more difficult it gets. And this is kind of what happened in what we're working. That so maybe it's so this is a work in progress, but so it's we're working with mean dimension with Jonathan. And actually, we're working with Sophic. So if you, yes, in our proof, putting Sophic for the lower bound was easy, but putting Sophic for the upper bound was when it got tricky.
Okay, any other questions? If not, let's thank Felipe. And this is the end of the semester?
This is the last planet seminar of the semester, if you wish to organize something else.
Okay, so
I guess everybody knows that there is a conference in Łódź, or two conferences actually. Well, for example, Darji.
They are just,
yeah.
Yeah,
Sure.
that's
You know about that?
Yes, yeah, I know.